Welcome to the Peacademia course on the basics of semiconductors. This lecture will cover the energy diagram. Let's start. By the time you finish this lesson, you'll learn the orbital geometrical shapes, energy diagram, Afbau and Hund principles, and electron configuration. In the previous lecture, I talked about the energy level, sublevel, and orbital. I also talked about the electron position, electron spin, and 4 quantum numbers. As you remember, we came up with this model to represent an atom structure. This model is not a real model, but helps to conceptually explain some of the phenomena happening in an atom. If I rigorously take a look at a real atom, not the model, I can see the geometrical shapes of the orbitals. We already know that the orbitals are high probability clouds where the electrons can be found most of the time. We have an s orbital, 3p orbitals, each aligned with the x, y, or z axis, 5d orbitals, and so on. You remember, in addition to the angular momentum quantum number, we show the sublevels by the letters S, P, D, and F. You may now have some clue where these letters are coming from by looking at the orbitals. For example, the s orbital is called S because it looks like a sphere, or the p orbitals are called P because they are polarized. Here is a half view of the model we developed for the atom. There are numerous details, curved lines, ovals, electron spins, etc. Every time we discuss the electron energies, we cannot draw such a complicated shape or model. There should be a more convenient way. Let's rotate the model for 90 degrees so as the nucleus is positioned at the bottom. In terms of energy level, the nucleus is the reference point. If there is an electron attached to the nucleus, the electron has zero energy. By moving up, the energy increases. Since we are concerned about the electron energy, this model can be translated into an energy diagram. In this energy diagram, the y-axis is energy. Since at the moment we are talking about an isolated atom, the x-axis does not exist. However, as we can later see, the x-axis is the interatomic distance in materials. In the energy diagram, the small horizontal lines represent the orbitals. For example, the 2p sublevel has 3 orbitals. As a result, for the 2p sublevel, we have 3 dashed lines. In the atom model, the energy levels are placed in order. Let me explain this more precisely through an example. If you look at the third energy level, you cannot find a sublevel that has energy more than any sublevel in the fourth energy level. However, when you look at the energy diagram, you can see that the 3D sublevel has more energy than the 4S sublevel. It's confusing, isn't it? You may ask yourself, how are we showing the electron on the energy diagram? In the model, I showed the electrons by circles. The electron can spin in this direction or the opposite. So how can we show the electron and its direction on the energy diagram? Well, we have a very simple prescription to show the electron and its spin on the energy diagram. If the electron spins in this direction, we use the up arrow. And if the electron spins in the opposite direction, we show the down arrow. The first energy level has a sublevel, and the sublevel has only one orbital. We already know that each orbital can hold only 2 electrons only if they spin in the opposite directions. We can apply the same prescription to the 2s and 2p sublevel and any other energy level in the energy diagram. The energy diagram can be simplified even more to get rid of unnecessary details. In this energy diagram, all the energy levels and sublevels are coming in order. Since in the simplified energy diagram there is no small line to represent orbitals, here we distinguish orbitals by placing space between each pair of electrons. In 1s, we only have one orbital with two electrons, so no need to have any space. The same thing for 2s. But for 2p, we have three orbitals. Here is the first electron pair, the second pair, and third pair. Observe how the rest of the energy levels are filled up in this energy diagram. So far, you know what is the energy diagram. But what if someone gives you a silicon atom, as an example, and asks you to fill up the energy diagram? To be able to do so, I need to introduce two very important principles, Afbau and Hund. Afbau's principle says electrons fill the lower energy levels before filling higher energy levels. Hund's principle states if in an energy sublevel there are two or more orbitals, electrons spinning in the same direction fill orbitals singly, and then electrons spinning in the opposite direction fill the empty states in the orbitals. This sounds too wordy, I know. Let me give you an example. Let's fill up the energy diagram for the silicon atom. Silicon has 14 electrons. According to the Afbau's principle, I need to start filling up the energy, the diagram from the lowest energy available. That is 1s. I put the first electron, there is no other orbital. Then I put the second electron spinning down. Now that the 1s is filled, we need to migrate to 2s. Here we have one orbital. The first electron spins up, then I place the second electron that spins down. 2s is now filled. The next sublevel is 2p. Here we have three orbitals. According to Hund's principle, we first need to make sure that all the orbitals have at least one electron, and then we can place the second electron in them. One electron for the first orbital, one electron for the second orbital, and one electron for the third orbital. Now I'm allowed to put the paired electrons in the orbitals. The 2p is filled now. Before I continue, pause the video and fill up the rest of the energy diagram yourself. I wait a bit. Well, I assume that you did the practice. Let's see if you made it correctly. 3s is filled like this. 3p is really interesting since by filling up 3p you can understand the real meaning of the Hund's principle. So far 12 electrons out of 14 have occupied empty states. We are now left with two electrons. One electron spinning up goes to the first orbital, and the other one which spins up again goes to the second orbital. That's it. We ran out of electrons. Let's fill up another energy diagram, this time for germanium. Just look at the way this energy diagram is filled up. After all the discussions we had in this lecture, I have a question for you. Is there any way to show the way electrons occupy states in an atom? So far, I have shown you two methods, the graphical model and the energy diagram. It turns out that there is a third option, and that is the electron configuration. Here is the energy diagram of the silicon atom. We can translate this energy diagram into a written statement called the electron configuration. But how do I do that? To start, first write down all the sublevels filled partially or completely with electrons for silicon. I have 1s, 2s, 2p, 3s, and 3p. Now, on top of each sublevel, write down the number of electrons existing in that sublevel. In 1s, I have 2 electrons, 2s has 2 electrons, 2p has 6 electrons, 3s has 2 electrons, and 2p has 2 electrons. Well done. What I just wrote down here is called the electron configuration. Let's do it for the germanium atom. Here we have the germanium atom energy diagram. Pause the video and write the germanium electron configuration yourself before I show it to you. Are you done? Well, the electron configuration for the germanium atom is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p2. In this lecture, I talked about the orbital geometrical shapes, energy diagram, Afbau and Hund's principles, and electron configuration. In the next lecture, I will cover the energy band. Thanks for joining another lecture of Peacademia.